It's a great honor to have today's speaker, Professor Misao Sasaki. He's really leading expert on cosmology, high energy physics theory. That's why he has many affiliations there.
Many.
So he started Unexplored gravitational waves on intergalactic scales.
Okay, thank you very much. Thanks for the introduction, and also thanks for the invitation. I was here maybe more than 10, 15 years ago, but I almost forgot everything. When I arrived at the metro station, and it was surrounded by something which I haven't seen, so I couldn't find out which direction. But eventually, I found some way to come here. It was nice to come back. Anyway, let me start. So this is something which I thought was quite interesting, although maybe some of you may not, but is that okay, let me just start. Okay. Oh, by the way, about this affiliation. So I actually was retired from Yukawa Institute in Kyoto, and after that, the KWIP hired me for a few years. And so I have one more year, but then APCP asked me to direct the institute. So I started the directorship presidency from this April, and they keep me very busy. Yeah, I thought it was less busy, but no, maybe it's just in the beginning. But anyway. About the cost part, Taiwan, I used to go there every year, but now I'm not going so often. But one time when I went there, he's not from this the cost part. He belongs to the AJAA, this Academia Sinica Institute for the Astronomy, and so I took that the occasion to collaborate with him. This is the result of this one. This is about the gravitational wave cosmology. As you probably know that about already 10 years ago, the first gravitational waves were directly detected by this LIGO, and everybody started talking about the gravitational wave cosmology, and which has become one of the most important sort of hot topics in the cosmology now. And it sort of provides new windows to explore the universe. But essentially, well, apart from maybe very high frequency modes, which are sort of future issues, most of the gravitational waves of gravitational wave astronomy are focused on, say, 100 hertz down to maybe -8 hertz. And the low frequency part is this another one is partial timing error. A detection of gravitational wave was a bit of past a couple of years ago. Nobody knows whether it was real gravitational wave or something else. Well, we don't know. But anyway, something is going on there, and the high frequency for part up to 100 or maybe 1,000 hertz. There are lots of future projects and plans and so on and so forth. Or if you go down to very, very low frequency, below, say, 10 to minus 16 hertz, which is just close to a period is close to the age of the universe, then we start to see this CMB, cosmic microwave background. And since if the wavelength is that size, that means the period. So period is the age of the universe means that you never see the oscillations, but you see some fixed pattern on CMB sky, and which is reflected the so-called B mode of CMB, and people are trying to search for that, and this is in this range. But apparently there are not any plan or anything what going on this, let's say 10 minus 15 to 10 minus 10 as this area. This is the intergalactic area and completely empty. And so I thought maybe even though you may not, you may have a sort of, let's say, normal inflationary theory. The prediction is this green line here. This is so in this case, you don't really expect any huge gravitational waves on this region. So normally people think that it's completely empty space. But nobody knows. Huh? You may have some interesting early universe history, and I will show you one of the examples, which might give rise to some very high peak gravitational wave in these regions. So why not consider? So here, my focus is not entirely on the whole regions, but one part of this region. Let's say from 1 to 100 megaparsec. Or in terms of frequency, 10 minus 14, 10 minus 16 hertz. Important thing is still, if you take the inverse of this, the period is like how say million, 10, 100 million, 100 million years. Yes, 0.1 giga years, something. Yes, 0.1 giga year. So for us, it's completely frozen when you try to see. So that's the interesting thing. By the way, this is before we go to this. Let me talk about the source thing. As I said, in the conventional inflationary gravitational wave is too small because the amplitude on so-called superhorizon scale when they are created is about 10 minus 5, which is the same as CMP. But in the case of scalar perturbations, this amplitude stays constant, even when they come inside our horizon and start forming all the gravitational cluster of galaxy and so on, so forth, galaxy stars and so on. So amplitude of this is just the Newtonian potential. Is 10 to the minus 5. By the way, nothing to do with my story. People usually think that the nonlinear effect would, create more stronger gravitational sort of a structure, but actually it's not. But this is 10 minus 5 is huge. In terms of the equivalence in the velocity, it's like 10,000 kilometers per second or something. But even this largest cluster of galaxies is like a few thousand kilometers per second level, or a gravitational potential 10 minus 6. And the gravitational potential of the galaxy is like 10 to the minus 7. So nonlinear structure tends to weaken the gravity. Density perturbation grows, but the amplitude of gravity, gravitational amplitude decrease, except maybe for some very tiny regions where you may form neutrons and black holes. Then this becomes order 1. But apart from that, actually nonlinear structure makes the gravitational perturbation small. And this is not so well known, so maybe it's a nice thing to know. In the case of tensor perturbations, even if the original amplitude is 10 minus 5, they oscillate. Oscillation is the characteristic of gravitational wave, but because of oscillations, they damp out, like inversely proportional scale factor. So if you consider some scale much smaller than the horizon scale, the amplitude will be reduced by this factor, which can be very small. So in conventional inflation gravitational wave, probably is too small to be detected because it's order maybe 1,000 smaller than something the scalar things and so on and so forth. But actually, there are some if you have some non-trivial theories in the early universe, this is what people call if you just consider the effective field theory. Effective field theory in cosmology means that you don't care what kind of theory you have, just assume that there are some, high energy theory, and then expand according to some guiding principles. Most simply, it's just the maybe because the universe is counting, you lose this time translation invariance, but just assume spatial translation invariance and so on and so forth. Under that assumption, what's the most general coupling and so on and so forth? And in this case, what if there are some non-trivial tensor field in the early universe? Then tensor can couple directly to tensor, our tensor, the HIJ, which is the gravitational wave. So you know, the people these days consider the so-called induced gravitational waves, but usually induced gravitational waves are at second order of say either scalar or tensor, because vector, because tensor is the two indices quantity cannot be constructed linearly from a scalar, because if you do that, you know, this has the transverse traceless property. So if you do the integration by parts, you know, you have the transverse component applying on this and it just disappears. So you cannot have the scalar linear vector coupling, but tensor can linearly couple. So this means that if for some reason this Tij unknown tensor field was excited in the early universe, this directly excited.
So, excuse me, in the language of particle physics, you're just assuming that there is a spin to.
That's right.
Exotic particle.
Yes, can be anything. Yes, yes. One of the typical scenarios based on this massive gravity theories, and the massive gravity, the covariant massive gravity. So what was the name? The Gavadaz, the Lam, blah blah blah. Some people, you know, they made some covariant theory of massive gravity, but the price they had to pay is they have to introduce some base metric, just some metric which is completely fixed, and they are sort of fixed by ad hoc in other way. But then, of course, people start thinking, why don't you make it dynamical? So you essentially have two copies of gravity, the one for us, one in some other sort of behind the scene, but they may have coupling. So this is something, you know, you can expect, for example. Yeah, but anyway, so this is well, I don't really know about the effectivity theory, so I just trust him. This is my collaborator. He's now in Dijon, IBS. And he told me that for various considerations, this is the leading of the term. Okay, so I trust him. So we computed if we have some amplification Tij, what would happen to Hij? And this is
normally sorry, linearized metric just coupled to energy momentum tensor generically. So I mean, I would identify as an energy momentum tensor.
Yeah. So that's the normal thing. In that case, energy momentum tensor would have usually in this quadratic form, right? So it's in the second order, but this is a linear order.
You are saying T is some fundamental field.
Yeah, something. As I said, maybe it's the some other the tensor field of the other universe. Yes. You know, we are not asking what theory can give this or not. Of course, in the end, eventually you have to answer this question. But just from this effective field theory point of view, what if there are some fundamental spin-two fields in the universe?
Yes, fundamental spin-two.
Yes.
Irreducible representation.
Yeah, that's right. Yes. And then in addition, now this is in preparation, but we are considering the possibility of parity violating terms. It happens that it is possible at the linear order, and which can also give rise to interesting parity violating signals. But since it's in preparation, I can show you the result yet. Anyway, the point is that so in principle you can excite this our gravitational wave to a very high amplitude. For example, this right-hand side, this is the log of the so-called gravitational wave energy density, normalized energy density, and usually this inflationary gravitational wave, it's an order or less than 10⁻⁸. If you square it, it's 10⁻16. That's the about the line of the what you would expect from the standard inflation model. But of course, you can do this enhancement. In this case, like 10 to the 5 times or squared, because it's squared amplitude, but its amplitude would be 10 to the 5 times. Which, if that happens, actually this would be bigger than scalar. Yes, this is still in principle possible. And here this scale is completely arbitrary. But if you assume, for example, this to be 1 megaparsec, this is a 10 megaparsec, 100 megaparsec, 1,000. So this application would not affect any large-scale observations, but could be actually present there. So of course, I mean this is sort of a wishful thinking, but at least if there is a possibility, you should do some experiment to if there's anything like this in this region of the frequency.
So alpha is a coefficient.
Oh yeah, this coefficient.
So if it's negative, you still have damping.
I forgot whether no. I think it doesn't independ. It's essentially independent of the sign. Yeah, if I remember correctly, yes. It may have some slight difference, but or maybe this the oscillator behavior may be different, but I think it's essentially the same. Yes. It doesn't.
Some question.
Yes.
So if we have some linear term Tij and H altogether quadratic, then can usually in field theory, by redefining the fields, can we diagonalize? In other words, getting rid of the linear term Tij by absorbing into the redefinition of Hij, let's say.
No. So Tij itself has the independent kinetic term, so you cannot do that. This is completely independent field. You have the action of Tij, action of Hij, and coupling. Okay, is that the what you? Sorry. Hello. We lost him. It sounded like
yeah. Okay, Misao. So my question is, we have a quadratic piece of Tij, quadratic piece of Hij, then the coupling, the quadratic coupling of T times H.
Right.
So in that case, by rediagonalization, we may be able to get rid of that.
So you will have two. It's a diagonalized modes, just like the case of those neutrino oscillation type things. And this period comes from partly because of these oscillations. Yes, the amplification happens, but depending on the scale and amplitude, you may have this sort of oscillation of the energy transfer to one to the other. Yeah, so in the beginning you have the energy in the Tij, but it transferred in Hij and transferred back in Tij and so on. You will see these oscillations. Yes.
I see. And what was the main reason why the scalars are ruled out, or it should be only coupling to tensor? What was the reason?
No. Scalar can be, but if you have the scalar, then scalar must be quadratic. Because if this is if it is just derivative of scalar, then if you do the integration by parts, you have the divergence of Hij, which must be vanishing. So you don't have any coupling at the linear order.
I see. Okay, I understand. Okay, thank you.
Okay, thank you. So at least there is some reason. At least if there nobody has explored that region, why not? Okay. Yeah. Oh, yes. So let me just briefly talk about this gravitational waves again. Maybe you don't. I don't need to explain this, but the gravitational waves essentially is the dynamical tidal force. Yes, it is represented by the some component of Riemann tensor, and which sort of squeezes or pushes, this kind of oscillations, quadrupolar oscillations, and this is the kind of a picture. The quick difference is so it is waves. Difference is that it's time dependent, but from the point of view of, let's say, galaxy, or even from us, galactic dynamical time scales at most like 10 million years or something, or maybe a little bit bigger, but not so large. It's about a gravitational wave in this frequency, 10 to minus 15 hertz. Like, as I said, maybe like 1 giga-year. For 1 giga-year, the galaxy, from looking from the dynamics of galaxy, this is static, which means essentially locally it is identical to scalar. Yes, scalar tidal force. There's no difference between tensor and scalar, looking from this local point of view. Yes. The only difference that if you look far down and see the difference between different redshift, let's say, then you have to you will see the difference. Especially, for example, in the linear theory, in the simplest case, usually if the scale is 100 megaparsec, the linear theory is supposed to be very good. So on those scales, the gravitational potential is independent of time, as I explained a few slides ago. So even if for the different time, this power spectrum essentially is of course independent of time and just given by the frequency or the wave number. However, in the case of gravitational wave, they have non-trivial time dependence. And non-trivial time dependence comes from these oscillations. So that's the difference. So this tells you if we know some way to measure the tidal force or tidal formation of galaxies, then we may be able to actually detect the gravitational wave on that scale. You see. Okay, so oops. Now let me just briefly go through the what are those tidal force fields are. So as usual, well here I'm just focusing on linear theory. You have in case linear gravitational potential. You have some scalar curvature term, which is if there's no anisotropy stress anything, then which is equivalent to this Newtonian potential. And you have the tensor, which essentially represent gravitational waves. I'm ignoring the vector because in the GR, at least in GR, or the say we think that our universe, in the current universe, probably is very well approximated by GR, except maybe you may have some additional scalar, but let's assume that there's no vector component. Yes. Then they see we have scalar and tensor. And the tidal force field is essentially, as I explained in the beginning, that it's component Riemann tensor, essentially the space-time component, which gives you this deformation of the quantity. There are this sort of a diagonal component, but the diagonal component is not so easy to. This is a breathing mode, sort of not easy to see anyway. And also, this is, as you can see, completely dominated by the scalar form. Forget about this. Then traceless part we call it tidal force. And then you can just make it dimensionless, and then decompose into scalar and tensor component. Scalar part is given by the scalar derivative of the Newtonian potential divided by essentially the Hubble parameter square. This essentially turns out the delta rho over rho, so density perturbation in the case of scalar. The tensor perturbation, on the other hand, is a second derivative plus some, this is the conformal Hubble parameter, anyway, some expansion effect. But on scales much, say, shorter than, smaller than the Hubble scale, and which is the case of our interest. Let's say if you assume this K to be 1 megaparsec inverse, 100 megaparsec inverse, then this K over H is 40 to 4,000. So at least at first order, this can be ignored. This is few percent contribution, or less. So you can just assume this. Then if you take the second derivative, the K square appears, and you get this effect. So as you see that maybe it's not so easy to see, but this component, this coefficient actually grows, but this Hij decays out. Therefore, Dij actually can never be so large. While in the case of a scalar, this is the density perturbation, which grows like scale factor. So eventually this dominates, but still there may be some possibility to have some tensor component on the, say, intergalactic scales. Now, since we want to discuss the parity violation as well, and also to, propose something new, then we found this that if you define the star operation, which is just the first derivative, kind of rotation of the original tensor field, if you take the rotation of this, or curve, you say, then interesting thing that if you just look at each sort of Fourier component, and you have this right sort of a circular polarization and left circular polarization, so originally you have the right plus left. If you apply this, apart from this, because of the derivative, you have an additional K appearing in front, but the sign changes. R parity, R helicity. Helicity remains as it is, but left helicity changes sign. So this means that if you take some correlation between Hij and star Ij, you will see the parity variation as well. So this is an interesting sort of, and apparently, as you can see, this is a local quantity, which is an interesting thing. I think we thought that it was interesting. Anyway, so then you just take just forget about the how to observe, but just focus on the theory first. Then if you take the 2-point function in the Fourier space, then for the two different sort of polarizations, then each polarization you have the standard sort of power spectrum, and if you take the star H, as I said, except for the additional K factor, you have the power spectrum, total power spectrum times some current factor. Chi is defined by this. This is just rewriting this one in terms of this total times some difference. Then apparently you see that this chi shows the degrees of parity variation. So in the largest sort of parity variation, if the R is 0, this is -1. If L is 0, this is +1. So this quantity is from -1 to +1, and if it is deviates from 0, then it signifies the parity variation. Anyway.
So some question, yes. Simple question. So the question is about the parity violation.
Yes.
Is it due to the background?
Oh, no, since I cannot show you the original action, but as I have just mentioned here, we may introduce parity violating interaction from the effective field theory point of view, and which is still linear. Yes. So this paper will hopefully appear within a couple of weeks.
So roughly, how does it look like, the parity violating term? Is it R?
No. It's essentially you have the epsilon tensor just appearing in maybe twice. I forgot. No. If it is twice, then it goes back. Huh? Yeah. Anyway, don't ask me too much. I mean, I'm not allowed to talk about this until they.
IJKTIJHLK, something like
probably something similar. Yes, probably. Yeah. Anyway, we did find that. Oops. So you may have linear coupling. Yes, linear order coupling, which can violate a parity.
This is intrinsic of the coupling. It's not the background.
No, that's right. It's not background. It's the intrinsic. Yes, linear order coupling. Okay.
Okay, so you simply drop the parity violating the interaction strength. Right?
Yeah. So then you from this sort of effective field theory philosophy, the coupling constant is arbitrary. But of course, a concern by observations or maybe theoretical consideration. For example, you shouldn't have any ghost modes, or you shouldn't. This theory shouldn't be unstable and so on. So forth. Apart from such a constraint, the parameters are essentially free.
Okay.
Yes. And so if somebody comes up with some real sort of UV nice theory, the full theory, I would be very, very happy. Yes. Anyway, so where are we? What? Oh no, which way? This, yes. Okay. So this is what I was saying, that is next page. Huh? Oh, what's going on? Yes. One important thing. So as I said, forget about the all this tidal force field and so on. So forth. Just compute theoretically the 2-point function. Then for this small scale much smaller than horizon, because when the gravitational wave propagate, they will be sort of essentially scattered by those inhomogeneities. This gives rise to some small but finite phase shift in the wave. And if you have such a phase shift, and if you sort of superimpose all everything, then essentially they are random stochastic. They become random stochastic field with random phase, and because of that, even if this was given from some inflationary stage with some very highly correlated phase and so on and so forth, you have this nice uncorrelation between the different sort of case, and which gives rise to the very, very simple cosine behavior in time. So this eta is the conformal time. But anyway, so apart from this the scale factor dependence, which just is because of the damping, adiabatic damping to the oscillations, you have this correlation, 2-point correlation function for different time has this cosine behavior, which is the difference from the scalar case. So the question is, can we actually observe? And actually, there is already sort of theories and observations, which is of so-called intrinsic alignment of galaxy, and which is the well, there's kind of gravitational lensing effect. If you have maybe you have seen some picture of gravitational lensing, and because of the existence of say lens galaxy, all this image of galaxies tend to sort of elongated around this so-called Einstein ring type things. And this is apparent in alignment. It is called because it's due to gravitational lensing. But what people found in those people working on large-scale structure is actually you can detect the so-called intrinsic alignment, which means that you can get rid of, if you can get rid of this apparent alignment, there still remains some intrinsic alignment, which is due to tidal force. Because of the tidal deformation, tidal force, those galaxies tends to be aligned in certain directions on large scale. And they found, I mean, well, this is the first paper, but there are tons of papers there. Although this amplitude is about 10% of the gravitational lensing, but still they start, well, apparently they say that they can detect, and they are starting to detect this intrinsic alignment, and which also gives rise to very important information, structure formation, and so on. Now our task is on gravitational. So in this sense, you have some this tidal force field, as I said, and this gamma ij is the deformation tensor of the galaxies, so if you have some tidal force field, then you have some you see some actually the deformation of the galaxy, and the coefficient is usually called bias parameter and so on and so forth. I don't know what it is, but they compute it from numerical simulations and also fit with the data and so on and so forth. Similar thing can be done, and this was very recent, not recent, but maybe 10 years ago, that actually if you sort of put some tidal force field due to tensor, you also see some these deformations, and this, I don't know whether how big the difference between this B and this B, but they see you use a bit more. This is fairly, I think it's almost trivial, as I said, in the limit of a static gravitational tidal force field, the two sort of things are essentially the same. So I guess this is the same mode of this. But anyway, what they are saying is that they can actually detect this tidal deformation by looking at this intrinsic alignment. So there's a hope. Yes. Yes.
Maybe I'm missing something. You said the gravitational waves of our interest, its wavelength is smaller, even comparable to the size of the universe.
No. It's a bit smaller. Let's say it's like maybe 100. So 1% of the size of the total universe. But still, it's a 100 times bigger than the size of galaxies.
Yeah.
Yes.
Yeah, I was just confused because if the wavelength is scale of universe, then it cannot align something along some direction.
Even no. Yeah. If the entire universe is actually, if you have some how to say deformation of the gravitational wave or whatever on that scale, then you have a isotopic universe. Yeah. But we have a very strong constraint on that. Yes. Sure. Anyway, okay. So this is just purely technical. What we are interested in is, can we? I mean, of course, there are many sort of ways to detect these things, and combined with three-dimensional simulation and so on and so forth. But for the moment, just forget about all these things and focus on what we can observe observationally. Observationally, what we can observe is only those which are, how to say, perpendicular to the line of sight. Yes, this is called the projected field. But you have to project everything on two dimensions. But of course, you have another sort of a, I'll say, a observable towards the depth to this observer. So this means that they actually you call three-dimensional projection. The projected in 3 dimensions. No, three-dimensional quantity. They depend on 3 dimensions, but it is the projected field. But anyway, that's the observable. So these are all kind of technical things. You take the say line of sight. We are here and we are observing something by there as a z-axis, and x and y to be the orthogonal directions, and then you assume some propagation gravitational wave in some other direction, and then you just project everything on this xy plane. Yes. Then you obtain some quantity which corresponds to the projected tidal force field. So then you can extract out this parity component, parity even left and right, or even odd component, and there are several already not existing method which is called so-called ED decomposition. This is exactly like the case of B mode polarization of CMB, E mode polarization CMB, same thing. But and this is good because you don't have to take in special derivative anything. So you can just use the raw data on the project on the sphere. But the good point is that, but handicap or the bad point is that they are defined globally. So unless you have a very good sort of knowledge of what should be on globally in the whole space, they cannot be defined very well. For example, so this is kind of a ironical thing that in the CMB case you have this a galactic plane which you cannot observe and so on and so forth. So when they are trying to observe this B mode, they assume parity conservation, and if the parity is conserved, E cross B should be 0, and so they use this equal to 0 to calibrate the data. So in this sense, with this method, actually, it's not so easy to detect the parity variation because you don't really know how to calibrate whether it is B or E in a global sense. On the other hand, our method, this is a new method we are advocating, is that although you need this special derivatives, which means that you need even more precise accuracy in the local area of your observations. But point is that apart from this component, if you have the sufficiently enough data within the given volume of space or the project area, then you can clearly see the parity variation. So I'm not saying that the ours are much superior to the previous one, but I guess in the end we should probably combine these two. Yes, and to use the has advantage of each method so that you can get the most out of experimental observation data. But anyway, let me just proceed again. So remaining is a bit, even more technical. So I don't know how much I should spend time. But anyway, the whole point is that you construct divergence of this tidal force field tensor or rotation or divergence of rotation, and try to take the correlation function. Then you find, for example, if you take this rotation component, then you have some power spectrum times in something which is interesting to this quantity, which is essentially the kernel for this the 2-point function. But we, since this kind of kernel nowadays, especially in this pulsar timing array observations and so on, so forth, they call it overlap reduction function. So we just borrow that name. I don't really know the meaning of this, but it's a nice naming. So that's why we put this name. But the point is that this shows some characteristic behaviors. I can show you soon later. This is the case. So H star H. This gives you if this is non-vanishing, then this means that you have some parity violating component. And it has some particulars of this overlap reduction function. Anyway, so as I said, this is just, you can just compute this locally if you have sufficient data.
Locally, experimentally, what does it mean?
Means that, for example, if you look at some fixed region of the, say, the sky, and you have enough galaxies in that regions, then that's the local.
Is the signal the scale where you expect to see the signal related to the wavelengths of the?
Oh yeah. So let's say we're interested in wavelengths of 100 megaparsec or so. Then yeah, you probably need the scale of the which spans let's say 100 megaparsec. I don't really have a good intuition, but if you think that this is 1/40th of the Hubble size, then the naive linear thinking, this is a pi divided 40, which is like 10 degrees, I don't know, something like this. So you consider 10 degrees square in the sky. And if you have sufficiently large number of galaxies in that regions, then you can have this. So that's, I mean, local. But this EV thing, you need global data, yes. Anyway, so maybe I should go to the next page before I show this. So this is the interesting difference between scalar and the tensor tidal force. So scalar case, let's just like so low frequency or large wave number thing. In this case, essentially, the wavelength is very large compared to the scale of galaxies. Then there's no theta dependence. If you take some angles, they look same because within that angle, essentially the gravitational wavelength is larger than that wavelength in some sense. So it's essentially constant. But when this is the time difference, it goes if the time difference goes how to say large and large, it just monotonically decreases. Yes, this is because it's you lose correlations between these 2 points essentially.
So you're calculating the 2-point correlation function between galaxies at different times.
Different redshift, yes, that's right. That's the most important and interesting thing. While if you look at the tensor case, you see it oscillates. It is go down and up and down. Yeah, I mean, it's maybe not so easy to see from there, but for example, if you compare, let's say, 1.6 is here, it's going below 0, but 2.0 is up here. So it's actually oscillating. So this oscillation is the most important property of the gravitational wave compared to the scalar. So in our case, this is which has not, unfortunately, because in the case of scalar, because everybody is interested in sort of a spatial 2-point functions, and never consider this 2-point function in time. Probably because they know that it just simply goes die out. But if you take this 2-point function in time, then you use some kind of template of oscillatory template, then you may be actually able to detect this gravitational wave component from this tidal force. So that's our hope. Anyway, and this is the case between the difference between the say the standard gravitational wave signal to the parity violating gravitational wave signal. In this case, this 2-point function, the standard gravitational wave, as I said, it's just standard gives oscillation. But parity violating thing has a very special property that at sort of at the point where the when the angle as well as time difference goes to 0, it vanishes. This is because it's parity odd. Yes. So so in this sense, this theta dependence is very important for detecting parity violation. Yes, compared to the case of standard amplitude. And in this amplitude, of course, you have no vanishing. For example, in this case, you have some finite amplitude. When both angle and time goes to 0, 0-point origin is non-vanishing, but it's 0 here. So to summarize, what I have shown is that if you take any of those, if you take, maybe I didn't explain very carefully enough, but if you take divergence and rotation and divergence of the original tidal force field, then you can extract the gravitational wave locally. So the price to pay is that you do need lots of data so that you can take the spatial derivatives. But if you have such data, then you can actually see locally. Or maybe you can use this as a template to detect the gravitational waves. And take cross correlations, then we can actually detect the parity violating signals. And as I said, this is complementary to the method. And so probably if in the future, if somebody, we need somebody, next observer, who are interested in such things, then I would probably, or they would probably consider some way to combine these two methods so that you can make best out of their observational data. Anyway, right now we have no sort of quantitative prediction projections or future predictions and so on so forth. And this is because thanks to this guy who is my collaborator, who is from this Academia Sinica Astronomy Institute at the he thinks he can do sort of make some kind of a numerical estimate of this projection, and then we know at least first of all, since as I said, we don't have any constraint in this area, but we will be able to draw some line, observational upper bound at least, because if we see something that's tremendous discovery, but maybe I shouldn't expect too much. Thank you.